So now let's start a new chapter to talk about neural architecture research. So far, we've talked a lot about how to compress an existing model, right? I can prune, quantize it, reduce it, squeeze it. What about we design a small and compact neural net to begin with? Can we design a small and efficient model to begin with? And what are the building blocks? And what are the search strategies? Right? So that's what we're going to learn. So we will cover the basic concepts of neural architectures. Okay, what are the design principles? What are the building blocks? Just like you are trying to architect a building, what are the building blocks? Okay, what are some manual design principles? And then we are going to switch gear to talk about automatic design principles, how to automatically search efficient neural network architectures given a latency constraint, given an accuracy requirement. Okay, so the goal would be rather than like manual architecture design, we want to have this automated design approaches to save the time and also improve the productivity. So let's first talk about some basic concepts and design principles, okay, for neural network architectures. So let's first review the dimensions of different layers, like FC layer. Okay, so the dimension is basically input feature, C in channel, C out channel for output. So the weight is C in by C out. So the number of max for linear layer is just C in times C out. And then we have this convolution layer. This is just a review, so I will go relatively faster. Okay. So this is the dimension for 1D convolution and also for 2D convolution, right? We have input feature map, we have the weights, we have the output feature map. So the amount of computation for convolution is the product of the 6 terms, okay? C in C out, and the XY dimension for the kernel, and also the XY dimension for the weight. Okay? For the input image. Okay? So it's why it's 6 terms, because to produce each output pixel that require a page kW times C in this amount of computation. And in total, you have to compute CL times W and times H. That's why we multiply these 6 terms together. To reduce the computation, we remember we introduced this group convolution. Okay, so we break out this large layer into 2 smaller layers. Okay, so the number of weights will be divided by the number of groups. Okay. Similarly, for the computation, the total amount of max will also be divided by the number of groups. If you want to go on the extreme side of group convolution, where the number of groups equal to the number of channels, then we have this depth-wise convolution. Okay, so for depth-wise convolution, the number of weights is very small, only C times the KH and KW. So the amount of computation for depth-wise convolution, we have just C out, we don't have C in. Okay, so just multiply these 5 terms together for depth-wise convolution. And finally, we have this 1-by-1 convolution. Okay, 1-by-1 means the KH and the KW are both 1. Okay, so it doesn't have this spatial feature learning capability, but it can combine the information across different channels. So with these, we can build neural networks on top of these building blocks. So let's first introduce several concepts. The first is stage. Okay, so a neural network architecture consists of the input stem, which is usually a large kernel to increase the receptive field, since this is the first layer with high resolution. So the number of channels is really pretty low, okay, so that we don't have a lot of computation over here. And usually, this is a strided convolution and then followed by a pruning, which can aggressively downsample the resolution from 224 to something like 56. Okay, and then we have several stages. So here we have 4 stages. Okay, within each stage, the resolution is the same, right? For example, in stage 1, we have 56 resolution. Stage 2, 56. Stage 3 is 28. Okay? Stage 4 is 14. So, and after that, the head is application specific, right? For detection, you have detection head. For segmentation, you have segmentation head. And if you want to do multiple tasks, you can have a head for each task. Okay. So that's the definition for the STEM, input STEM, the stage, and also the head. Okay. So we have these downsample layers, which is quite popular in neural nets, where you can observe the number of channels are growing. Okay? So initially, we have only 3 channels in the input, and then 64, 256, 5, 12, and then 1K. Okay? So we are increasing the number of channels, but decreasing the resolution. Okay? So downsample is usually done at the first block in each stage, okay, via the strided convolution or pooling. So we introduced the pooling. We can either do max pooling or average pooling. Okay. And then we have these residual connections within the stage. Since the resolution from the input and the output is the same. Okay? The number of channels matches. Therefore, we can directly have this additive wise operation to have this bypass layer, which we are going to introduce later. Why we use that? So this is showing before and after adding this residual and skip connection. What happens for the error rate? Okay? So we want to switch from 18-layer network to a 34-layer network. We want to increase the capacity, hopefully to get a lower error rate. However, if we naively just increase the number of layers, the error didn't decrease, but actually increased. Okay. But if we add such bypass layer, actually the deeper the layer, the lower the error rate which we want to go. So this residual or this skip connection really helps with this optimization. So here are a couple of manually designed neural nets, starting from AnexNet, right? So AnexNet introduced a very large kernel in the beginning stages, like 11x11 convolution, 5x5 convolution. Okay? Since the number of channel is usually smaller, therefore we can afford to have larger kernel sizes. So it's also a breakthrough that is the recent development of modern deep learning architectures. Okay, and then we have this VGG network.
Is residual connection, is it like mathematically proven that if we add them, it will help the deeper network, or does it just work on the specific data set? No?
It's empirical. It's empirical. It works. But so far, if you run neural nets, pretty much all the neural nets have these bypass layers, which is so popular, very widely adopted, but it's empirical. Okay, so VGG adopts only 3x3 convolution. Okay, so it doesn't have 5x5 with the principle that if you have you have two 3x3 convolution, what is the receptive field? So from two consecutive 3x3 convolution, you have a receptive field of 5, right? So in order to achieve the same receptive field, two layers of 3x3 convolution require only 18 weights. Assume only one channel, right? But you have one 5x5 convolution that requires 25 parameters. Okay, so this is assumption from VGG that stacking multiple small kernels is better than just a single large kernel. Is there any drawback for replacing one 5x5 by two 3x3 layers.
Is it slower now that I want to do two?
Yeah, so it introduces another layer, right? Another kernel call and another activation. You have to store the activation and then load the activation again. So that's something we need to consider when we are making the network deeper. Right? Not only do we care about the number of parameters or implementation blocks, right? But also we do care about the number of intermediate activations, right? And also the memory movement. Especially when we are doing training, we have to store all the intermediate activations in memory for backpropagation. So if we have only one 5x5 layer, we just need to store one intermediate activation for training. But if we have two 3x3 layers, we have to store two intermediate activations, okay, which almost doubles the amount of memory. So the image accuracy error rate is keep decreasing from NXNet to VGGNet. So later, people want to design those small and compact neural nets. So that comes to the SqueezeNet. Okay, so replacing 3x3 convolution with the FIRE modules, and also use this global average pooling in the head to reduce the area, the overhead of the head. Okay, so global average pooling is basically pool over the XY dimension to have a single one by channel tensor. So here, since we have 1,000 classes, the channel number is 1,000 in the last layer. So SqueezeNet basically passes the input tensor into a 1x1 convolution. Okay, and shrinks the amount of channels by 4 times. And we pass it through a 1x1 convolution and 3x3 convolution, and then lift the amount of channels. Okay, and finally concatenate these two branches. So we introduced before, we can reduce the model size from NXNet to 40 megabytes all the way to only 0.47 megabytes, less than half a megabyte, which is pretty small. So at that time, when I design and test the latency for this model, we find it actually not much faster than NXNet, right? So what could be the reason? Remember, we talked about many different aspects for evaluating a neural net, right? So the model size is not the only thing that matters about the latency, right? We also want to care about the amount of data movement, the amount of activations, right? Number of flops. So we have to take all the considerations into our design. Okay, and then in 2015, 2016, we have this Resnet. In Resnet, basically have two important design principles. One is introducing this bypass layer, which nowadays pretty much all the very deep neural nets have such bypass layer. But however, there's another way that we can move such bypass layer merge it into the convolution layer to make VGG great again. So some recent papers use the reverse ideas, but this is a very popular idea, okay? Introducing the bypass layer. And also it reduced the number of channels by 4x before running this 3x3 convolution, okay? And we reduce the feature map with fewer number of channels from 2K to 512 to the 3x3 convolution, and then expand the number of channels in the 1x1 convolution. So how many flops do we have? Okay, so in this first 1x1 convolution, this is the amount of computation, right? Input channel, output channel, HW, kernel is 1x1. And then for this layer, since we have less channels, so this is the computation. Adding them up together, that's 512 by 512 by HW 17. Compared with if we directly have just one 3x3 convolution from 2K to 2K channels, okay? So that will be 8.5 more flops compared with using such bottleneck structure. Okay, so that's the design principle of this bottleneck layer. And then people propose this Resnet introducing group convolution. So in the beginning of the lecture, we reviewed this group convolution, which basically have multiple convolutions. For example, in the first neural net, we cast 256 channels to 128, and then map from 128 to 128, and then lift the number of channels from 128 to 256. And if we apply this group convolution, okay, so we have much smaller number of channels, only 4 channels, okay, but we have 32 of them. So 4 multiplied by 32, we still have 128 output channels. Okay, so we do such 1 by 1, followed by 3 by 3 convolution separately. Okay. So all these can be done independently without talking to each other. So the final 1 by 1 convolution from 128 to 256 channels can be also decomposed into 32 smaller 1 by 1 convolutions that maps from 4 channels to 256 channels. Okay. So this is an illustration. What is a group convolution? Okay, so we have many identical groups of convolution. So which one is more hardware friendly? This one or the one on the right hand side? Actually, it's this one because we have more fewer number of kernel calls. So functionally, they are the same. You have the group convolution, but here you have just one big 1 by 1 convolution. But here you have 32 much smaller convolutions, which will lead to low GPU utilization. So it's always good to have a fewer number of kernel calls, but large kernel calls, like 256 by 128 compared with 256 by 4. Okay? And similar for the bottom 1 by 1 convolution, it's better to have a single 128 by 256 rather than many 4 to 256 1 by 1 convolutions. Yeah, so that's a design principle. But recently, there are several research that can automatically map or convert or fuse those kind of complicated computation graphs to such simpler computation graphs. So that's some principle to keep in mind. All right, so in 2016, 2017, people proposed this mobile net targeting mobile devices. Okay, so by utilizing this depth-wise convolution. Okay, depth-wise convolution is an extreme case for the group convolution where the number of groups equal to the number of channels. Okay, so in this example, we have depth-wise convolution to capture those spatial information, but it doesn't merge the information across different channels. Okay, so how do we do about that? Between different channels, how do we merge the information across channels? We can use 1 by 1 convolution. Okay, so we have this separable convolution. So the depth-wise conv is responsible for this spatial modeling, and such 1 by 1 convolution is responsible for merging the information across different channels. So after the first version, the second version of MobileNet proposed this inverted bottleneck using the intuition that the depth-wise convolution have much lower capacity compared with the normal convolution, right? So how do we compensate that? We just increase the number of channels. So in this case, after this 1 by 1 convolution, remember in Resnet, we actually decreased the number of channels before. That's called the bottleneck layer. For the inverted bottleneck layer, we are expanding the number of channels, say by 6. Okay, so for the depth-wise convolution, we have a much larger number of input channels. And after depth-first convolution, we use another one-by-one convolution to project number of channels back to n, so that we can have this bypass layer from n to n. Okay, so this is the idea for inverted bottleneck. It contains 3 layers. Okay, about 1x1 count, n channels, a 3x3 depth, so it's count 6 n channels, and another 1x1 convolution from 6n back to n channels. Okay, so that's a building block for mobile V2. And this network is was super popular in the past couple of years when we are using mobile CPUs, Raspberry Pis, etc. Those low computation capability devices. But with the recent advancement for deep learning accelerator, the utilization of such depth-wise layer is not as high as the normal convolution. So recently, there's another trend shifting back to this Resnet-like without those depth-wise convolution architectures. So the area is just moving so fast, and the design is always concerning both the number of the accuracy and also the hardware efficiency. And the neural network design is always coupled with the neural network hardware design. Okay, so since for 3x3 convolution, we can have this group-wise convolution. How about this 1x1 convolution? Okay. Can we have group conv for 1x1 as well? The answer is yes. So in this original net, we have 1x1 convolution, but we want to turn it into group-wise convolution. Okay, and then what happens for group-wise convolution? So this is the channel dimension. Okay, in this case, we have 3 groups. Each group just run this 1x1 convolution with itself. So there is no information flow across different groups. Okay, so the feature learned from this output purely comes from this 1/3 of the input. Is that a good phenomenon? Of course not. We want to make sure we have a bigger scope, right? We want to have the information across all the channels. So how do we do that? We can introduce this channel shuffle operation, okay, which 1/3 of the first group comes from 1/3 comes from group 1, 1/3 comes from group 2, and the last third actually comes from group 3. So this is the shuffle information. Similarly, for the group 2, 1/3 comes from the first group, 1/3 from the second group, last third coming from the last group. So in this way, the final output depends on all the input channels, all the groups, rather than only the first group in this case. But the drawback, again, data movement, right? Sometimes there's a trade-off. But people can smartly do that by shifting the pointers. So this is a big picture we introduced so far. We talk about Resnet, we talk about Resnet 101, Resnet. We also talk about this is MobileNet V2, much smaller, right? We also talk about MobileNet V1. So from V1 to V2, by introducing this inverted bottleneck, same latency, but much same max, but much higher accuracy, right? And the size of the circle basically indicates the number of parameters.
How certain are we that these techniques work on things beyond ImageNet, like classification problems that are not related to images? Maybe the question, but it seems like that's the gold standard for comparing these techniques.
I think ImageNet is has too many number of classes, right? In practice, not all the applications require like fine-grained classification of about like 2 very different flowers, right? And people not only care about the global information, but also local information, like, for example, segmentation is very important application nowadays. It's available in the new iOS, right? And also detection, very popular for autonomous driving tasks. So ImageNet is probably just something to benchmark to begin with, but the downstream tasks accuracy is something we really care. Sometimes there's indeed a difference between the ImageNet accuracy versus downstream task accuracy. We're going to learn that in the transfer learning section. So something performed well on ImageNet may not perform well on the downstream task. So you have to be careful when selecting the model on a specific task. Okay, so far we talked about many neural nets that are manually designed, right? So from AlexNet to VGG to Resnet to MobileNet, right? So we have to make a lot of decisions, the tuning, the number of channels, number of layers, okay, the connectivity, the resolution. And each time, in order to get the accuracy, we have to train the model, right? Model training is really pretty slow. It takes a lot of time, a lot of efforts. So is there a way to automatically search efficient architectures? So in comparison, we find these are models produced by neural architecture search for NAS. Okay? So everything with a round circle inside, those are handcrafted, hand-designed models. And those with asterisk in the middle, those are AutoML designed models. And here we find these AutoML designed models actually consistently outperform this human design, right? With much lower amount of computation and with higher accuracy. So let's start a journey to talk about neural architecture search. Okay, so here's the illustration of NAS. It has three critical components. Okay, we want to design a search space. What is the building blocks? What are the possible choices we can have? And then we have this search strategy. Okay, how do we search? How do we pick among this gigantic search space? Okay. And then after picking a design from the search space, we want to have a good performance estimation strategy. Okay, what properties do we care? Of course, we care about the accuracy. We also care about the latency, right? And sometimes we even care about the model size, since we want to upload the model to the App Store, and you don't want the user to take a super long time to download the model, right? We also care about the storage, right? For example, the recent language models, 175 billion parameters. Okay, even one GPU cannot fit such a large model, right? And also we care about the energy, right? Otherwise, our phone will soon run out of battery. Right? So those are the performance estimations. So we feed this performance estimation back to the search strategy and then propose another architecture and estimate the performance and then propose a new one. Okay, so that's the basic flow for neural architecture search. So the search space is a set of candidate neural network architectures. For example, in this case, in different stages, we can repeat this bottleneck block by 1 time, 2 times, 3 times. So that's an example for the search space. Okay, we can search between 2 blocks, 3 blocks, or 4 blocks. Okay, and the search strategy basically defines how to explore in the design space. We can randomly sample architecture, we can evolutionary, we can introduce that later. How do we select? And finally, for performance estimation, we can define what is a good model and what is not a good model. Okay. So let's first talk about the search space. And here we have 2 possible search spaces. One is on the cell level, each cell. Okay, the other is on the network level search space. So let's start by talking about the cell level search space. Okay, so this is a classical architecture on the ImageNet dataset. Okay, we have this input SAM. Okay, and we have this reduction cell followed by several normal cells. Okay, so this is showing we are repeating this normal cell by n times. okay, and followed by another reduction cell. Like we introduced in the beginning of the lecture, what is this reduction cell doing? Reducing the resolution, right? So here we are reducing the resolution, increasing the receptive field. So we have different cell architectures for the normal cell, where the input resolution and output resolution is the same, versus this reduction cell, where the input resolution is higher than the output resolution. So in the first paper of NAS, basically they use a RNN controller to generate the candidates, okay, for each cell using 5 different steps. Okay, so each time we first generate the first hidden state and the second hidden state. Okay, so here's a hidden layer A and layer B, which is basically the 2 operands. Okay, they can choose either from the previous layer or the layer before the previous layer. Okay, and then the RNN controller is going to select the operation for the first hidden state. Right, so here it could be a 3x3 convolution. It can also be a 2x2 max pooling. It can also be a 5x5 convolution or 2x2 average pooling, or even identity layer. Right, so we choose the operation for the first hidden state, and then choose it for the second hidden state. Okay, and finally we select a method to combine these hidden states. Okay, either using the element-wise add, or we can also use concat. So the question is, assuming we have 2 candidate inputs, okay, and then we have m candidate transformations for each state, okay, and we have n potential methods to combine these 2 states. What is the total amount of search possibilities if we have B such layers? So we have to decide these 5 items one by one, right? We have 2 possibilities here from the previous layer versus the layer before the previous layer. So 2 choices here, 2 choices here. And then we have m candidate operations, candidate operations here. Finally, we have the n potential operations to combine them. So we just multiply them together, right, to the power of B. Assuming we have m equal to 5, for example, we can have 3x3 count, 5x5 count, 2x2 average pool, 2x2 max pool, and identity. Okay, those are 5 different choices. So m equal to 5. And for B, we can have element-wise add, we can have concat. So multiply them together, we can have actually 10 to the 11 different design space. That's a lot of neural nets.
Can you maybe explain again what exactly is meant with 2 candidates? What are the candidates?
Yeah, that's a good question. So this is a good illustration. Okay, so the input of this layer can either come from the previous layer or the layer before the previous layer. So for this one, both inputs are coming from the previous layer. But for this block, one of them is coming from the layer before that. It's just manually designed to be like this. You can also have like 3 choices, like hi-2. All right, so this is a huge design space. Okay, imagine if you want to characterize whether it is good or not, you have to train a lot of neural nets, and that's take a huge amount of time. Right? So as a result, people have to train on a small data set, like scipher data set, right? And then repeat the building block, right? So using such proxy tasks. In the next lecture, we are going to talk about techniques to get rid of those proxy tasks, make the search super efficient. We don't have to train so many candidates, okay, to efficiently search the model. So let's see what does this algorithm find for us, and how does it differ from the neural networks we have seen so far? Okay, so this is a normal cell searched by NAS algorithm. This is the reduction cell. We can see it's highly irregular, right? We have the input can come from either the previous layer or the layer before that. And there are so many branches. Okay, and you can have either the add or concat, or even a combination of them, right? So what is the potential problem of running such neural networks? I think about two directions. One is the search cost. The other is the search, the hardware efficiency, the inference. So we already talked about the first aspect, right? We have to evaluate a lot of neural nets to collect the feedback, which require a huge amount of training time. And for inference, this model contains many different branches. You have to keep the dependency, right? You cannot easily free this piece of memory, right? Until all the consumers of this memory is done. Right? You have to keep it in memory after all this layer is done, rather than like reach GNAT, you finish one layer and throw the activation away, right? And it involves several small kernel calls at a time. Okay, so in practice, none of these architectures is actually used in production. And then we are going to learn about this hardware-aware neural architecture search techniques very soon. But this laid the foundation of neural architecture search, pointing out that such automatically designed models can even outperform the human designed models for its accuracy.
Is it the case that if you train something like the one on the right, it might be harder to prove that because you've got so many branches and it's rather irregular in shape?
This is very difficult to either do pruning or any surgery on this model because it has huge amount of dependencies. For example, if you prune this layer, okay, the channel, since it has so many dependencies, when your element wise add two different tensors, you have to make sure the channel number matches. So if you play tensor A by 20%, you have to prune tensor B by 20% as well. So such dependency is very difficult to trace. All right, let's return and continue our discussion about the NATs. Okay, the network level search space. Okay, so we not only want to decide what is in each cell, but also what is the number of cells we want to have, whether we have this one building block or two building blocks, repeat that. Okay, so this is a very common decision we have to make across many different design choices. Okay, so what is the number of n here, and what is the number of repeated n over there, and how many, what is the right amount of depth and the right amount of number of stages for each network. Okay, so those are the network level search space with a fixed topology. Okay, so more interestingly, when we have this resolution in the design space, which is very popular in pixel-wise prediction tasks, for example, for image segmentation, we want to first downsample the images and reduce the resolution, and this direction is the number of layers. Okay, so conventionally, there are several architectures. First downsample and then upsample. Okay, for example, different resolution. Some of the architectures downsample, upsample, downsample, and then upsample. Okay, so for the image classification, we just keep downsample. Okay, so in general, we can express the design space in this graph. Okay, so every path in this graph indicates a downsample and upsample strategy. Okay, so using this general representation, they can perform such network level search space with such kind of searchable topology. So in this method, people find this NAS FPN. So FPN stands for this feature pyramid network, which is very widely used in in object detection tasks. Okay, so what it does, basically, this was the human design. which is basically combining multiple resolutions, higher resolution all the way to lower resolution, and combine the information together. Okay, so you have the information. You can detect both large objects and also small objects in this method. So such mass-based approach find several drastically different decisions. Okay, so for example, this kind of IP architecture achieves about 7.5 average precision. You can see it's kind of random. Okay, we are feeding different resolutions to different stages. It's quite irregular. Actually, it's not quite hardware friendly. The highest average precision is achieved using this architecture. So it first, sometimes you said even upsample by 4 or 8 times, right? So the upsampling strategy is quite different from this very regular human design. So we have to use such techniques very carefully, right? So we have to balance between the accuracy versus the irregularity. Right? Imagine such different irregular topologies is very difficult to be efficiently deployed on hardware and difficult to parallelize, right? So that's something we'll introduce in the next lecture, how to make neural architecture research hardware aware and hardware efficient. Okay. All right, so the next topic is basically how do we design the design space? Okay. So there are several heuristics to find a better design space. First, narrow down the design space before you're going to do neural architecture research. It's just like finding, trying to find someone in a big forest. Okay, you first want to narrow down the search space you want to focus. Right? So a common approach introduced in this paper called Resnet is basically using this cumulative error distribution, okay, as a criteria for the search space quality. Okay, so here in this sample, we have 4 search spaces. And what does this colored line mean? So, for example, this blue line means, so here is the error. Okay, the lower the better, the error. And this is the cumulative probability. So this blue line means, so in this search space, 38.9% of the models searched in this space have more than 49.4 error rate. Okay, so this is about 49.4 error, and here we have about 38.9%, roughly 40%. Okay, roughly 40% of the models have more than about 49% error. What about if we move to this orange space? Okay, 38.7% of the models, okay, have more than 43.2% error. So which line is a better design space? Is it the blue line or is it the orange line? If we combine these 2 lines. Orange, yes. Why the orange line?
The model has less error.
Less error, yes. With the similar amount of probability, 38.9 versus 38.7, the orange design space has a much lower error compared with the blue design space. Okay, so in this way, we can filter away those bad design spaces. Okay. So what is the problem for this approach? Getting the error of a neural net is non-trivial, right? We have to train it. So we can train it for maybe a couple of epochs to save the time, but again, it takes time. So designing the design space is very important when you are trying to target a new design constraint. Okay, for example, the tiny machine learning microcontrollers, which has much smaller amount of memory compared with mobile AI and cloud AI, right? So from cloud AI to mobile AI, the memory is reduced by like 4 times, but the tiny AI is reduced by 3 orders of magnitude. So there's a big gap between what we want, that's like a few megabytes versus what we have, like a few hundred kilobytes. Right? So given such a completely new design space, it's even more crucial to find a good design space. For example, for tiny microcontrollers, we not only care about the latency energy, but also the memory. So initially, we are given a full network design space. Okay, and then we want to do such search space optimization to narrow down the design space. Okay, and then we are going to perform architecture search on such narrowed down smaller design space. Okay, so in this tiny neural architecture search, we propose this automated search space optimization. Okay, for such resource constrained specialization. And the intuition is that we don't want to waste a lot of time to train the model, get the error, and plot the figure. Instead, we use a very simple heuristic. Given the same memory constraint, say 256 kilobytes of memory. Okay? Computation is cheap, memory is expensive. If you can fit more computation given the same amount of memory budget, then that's considered a good design space. Okay? So we replaced the error rate with the flops. Okay? So the better the model, the better the design, the higher the number of flops that we can fit given the same memory constraints, the better the model, the better the design space. Okay. So for example, this red curve, so more than with 80% of the probability, okay, so this is 80%. Okay, so the amount of flops is more than 50 million versus for this black design space, okay, the number of flops we can accommodate using the same probability is only about 33. Okay. So we use this heuristic. You don't need to train the model. You just measure the flops given the same memory constraints, and you want to use the design space that can offer a likely to achieve higher flops under the same memory constraints, and you pick that design space as your search space. And how good is such approximation, right? We are approximating the accuracy by using the flops that we can fit given the same memory constraints. So actually, we find that the final trained model's accuracy matches quite well. The trend matches quite well with the amount of flops. Okay, so we can use these flops as a very cheap, very accurate estimator for the design space quality. Okay, so here we also compare the different search spaces, including the baseline is just the Resnet 18 okay, with 224 resolution. Using a randomly find a search space, you give an accuracy of 74.7. Okay. Sometimes, what about using a much bigger design space? So you want to find someone in a forest, you search the entire forest, even the forest next to it. It's not necessarily good because randomly sampled a huge space leads to even worse accuracy because it's harder to converge and the design space is too big. So the design space based on TinyML is actually outperforming all these different baselines by using such heuristic under the roofline model, right? Roofline model is basically characterizing the arithmetic intensity, right? But arithmetic intensity is defined by how much operation you can do given the same amount of memory movement. Okay? With the same memory movement, a good design space should be able to accommodate more flops under the same memory constraints. Okay? So if you don't have time to physically train the model to get the accuracy, you may as well use this simple heuristic, which is flops. Okay, given the same memory constraint to measure the quality of a design space. Okay, having talked about the search space, now let's talk about the search strategy. Okay, how do we iterate to find what is the next decision we have to make? Okay, the simplest one is basically grid search. you have several choices for the width, several choices for the resolution, and you have a grid. So you have 3 choices here, 3 choices here. You have a grid of 9 elements you want to try. Imagine you have more dimensions. Of course, this grid will become super large. And we want to filter out those bad designs, okay, by examining the latency constraints. Say these large models that has pretty big resolution, pretty big width, they can be pre-filtered without having to train them because they already breaks the latency constraints. Okay? And the idea is to train those remaining models to observe the latency and accuracy trade-off. Okay? So a practical work using grid search is actually the efficient net. Okay? So efficient net searches around different dimensions. So given a baseline, okay, you can search the width, scale the width, make it wider for each layer, but the depth is the same. It can also scale the depth. Okay, more number of layers, deeper models. It can also scale the resolution using bigger resolution. And compound scaling is basically saying we shouldn't push one of the choices to the extreme, but rather we need a systematic approach to scale different dimensions, okay, including the depth, the width, the resolution, okay, such that they multiply them together roughly. We can expand the model by 2 times. Therefore, the degree of freedom is actually 2 dimensions. So the 3rd dimension is constrained by this constraint. Okay, so given at that time Google has a lot of computation power, we can train each configuration from scratch to get the accuracy and latency. So it thoroughly searched the whole design space by using grid search to train each model. Okay. So are there smarter ways rather than grid search? Of course, you can do random search. And how does that perform? So this is the accuracy for random search. And this is compared with the smarter evolutionary search. Actually, random search is not too bad. Okay? Given enough iterations, random search achieved roughly 68.4%, compared with the evolutionary, just roughly gives 68.7%. They differ a little bit, but random search is actually a very strong 73.8 versus 74.3. In practice, in a lot of products, if you don't have to go to that extreme, but you want to make the product simple, easy to use, this random search is actually a quite strong baseline. And usually that is also used in publication to verify that you're actually doing the correct thing. And first try this random search on your search space. All right, and then let's talk about a more advanced search method, which is using reinforcement learning. Okay, so the challenge is that the accuracy is actually not differentiable, okay, objective. And then how do we update this RNN controller? Remember, we have to make different decisions for the neural nets, okay? Choosing the number of filters, height, width, stride, etc. Okay, so here we have this paper casts this problem into a reinforcement learning problem where it has a controller sample architecture with probability P, okay, and then train this child network and to get the accuracy as a reward. And then it used policy gradient to calculate the gradient with respect to P and scale it by R, the reward, to update the controller. Okay, so it uses this class reinforce algorithm to turn this P into something that is differentiable. That is also used widely used in many different other approaches, such as the proxylase mask, proxylase using interactive research, which we are going to introduce the motivation in the next lecture, which is a very efficient method. We have to train it only once rather than train it many times. But here, what I want to say is that you have these architectural parameters, okay, controlling the probability to sample different paths. Okay, and that is not differentiable because these parameters will be binarized either to 0 or 1, okay, indicating whether we are selecting this path or we are not selecting this path. Okay, so this binarization process is also non-differentiable, and it's possible to use reinforce to approximate the gradient with respect to the architectural parameters. So these are the architectural parameters we can use RL to learn. But in practice, RL is not easy to tune, okay? And the reproducibility makes it less popular, at least in our lab in recent projects. And for the sake of thoroughness, we also introduce this Bayesian optimization for neural architecture search, which is basically balancing this exploration and exploitation, and it has acquisition function to propose what is the next architecture to explore after the current one. If we want to have more exploration, or we will have more exploitation. Okay, that is also not quite widely used. A very widely used approach recently is this gradient-based search. Okay, so in this work called differentiable architecture search, we can give different choices of probability. Okay, we can give different weight for different. Say this is 3x3 column, 5x5, invented method. Okay, and during the architecture search, we have a weighted sum of different paths. Okay, so we compute 3 times the original computation. Okay, consider different paths, and we have a weighted sum of different approaches, exactly like this. Okay, so the good part is that we can finally make everything differentiable. Okay, we have the probability of different paths, so we just choose the highest one in the end. But the problem is that we have to store n times the activations in the memory. Okay, so that's the potential issue. Another gradient-based search is rather than keeping all the copies in the memory, how about we just sample a subset? Okay? For example, we sample the branch with the highest probability. Okay? So it alternatively updates both this weight parameter and also these architectural parameters. Okay, and makes it possible to calculate the gradients of those architectural parameters. And also we can make latency differentiable. For example, we have 4 different choices in this layer, 3x3, 5x5, identity pruning, and this is the probability of choosing each layer. So the expected latency will be a weighted sum of different building blocks, okay, with multiplied by alpha, beta, etc. So finally, the expected latency is a function of these architectural parameters. Okay, so therefore we can plug in the latency into the loss function, okay? And we can back propagate the gradient to this latency function, okay? Making latency differentiable, so that we can search a model not only give higher accuracy but also run fast. So this is gradient-based search. And by using proximity NAS, we can make latency differentiable. Another approach, actually, we find the most useful and most easy to use approach we highly recommend is using this evolutionary research. Okay? So given a network, we can mutate it, changing the number of depths, changing the number of layers, changing the number of channels, and also we can run crossover. So here is an example of the mutation and crossover. Say this is a network. Originally, this block has the depth of 3. Stage 2 also have depth of 3. After the mutation of the depth, the first stage can have only a depth of 2. Okay? And the second stage can have a depth of 4. Okay? So still within the design space, but it gets mutated. We can also mutate on the operator, for example, changing from this 3x3 convolution into this 5x5 convolution. Okay? similar for this one. Or even changing from 3x3 convolution into one single 7x7 convolution. And in this scenario, remember in VGG, people start to use very small kernels, and later people start to use larger kernels. Okay? The reason is exactly as we discussed. We want to care not only the weight, the number of parameters, the computation, but also the receptive field, and also the activation size and the number of layers. Right? So one 7x7 layer has the same receptive field by 3 layers of 3x3 convolution. Okay, so that saves the amount of intermediate activations. Okay, and also due to such inverted bottleneck layer in MobileNet, so the parallelism is actually pretty low. It has no parallelism across the channel dimension. Therefore, it's helpful to use slightly larger kernels, like 5x5 and 7x7, to provide more parallelism to keep to prevent the GPU from being hungry. Right. So those are some of the design choices. Okay. Always think about the hardware. Always think about the parallelism and efficiency while you are designing the models. Okay. Finally, we can do crossover. Okay. So we have this is our first choice. This is the mutated version. And after crossover, we can randomly choose one operator among the 2 choices from these 2 parents. And that is like the child. Okay. For example, for this layer, we decided to choose 7. And for this layer, we decided to choose the left one, 3x3. Okay. So some of them is coming from parent 1, some of them is actually coming from parent 2. And we are going to implement and actually experiment with such evolutionary research in lab 3, okay, and observe the accuracy keep increasing using such evolutionary search methods. All right, so in summary, in today's lecture, we introduced these basic concepts of these building blocks of manually designed models. Okay? And then we introduced what is neural architecture search, the search space, the search strategy. Okay? And in the next lecture, we are going to talk about training in NAS and hardware-aware NAS. In today's lecture, we already alluded many designs that is giving high accuracy but very low efficiency. Both the search efficiency, it takes super long time to search, 48,000 GPU hours. And then we'll tell the story when I just came to MIT, where we don't have a lot of GPUs. We cannot reproduce those search results from Google. Then we propose much efficient architecture search approaches. Even with just one machine, you can still perform neural architecture search. So we'll talk about that in the next lecture. So search efficiency versus the model, the model has to be efficient. Right? We want to physically deploy the model on the mobile phone microcontrollers rather than just having good accuracy. And recently, there are also new interesting directions of training-free NAS. So just don't require any training. You can pick which model is good, which model is not good. Okay? And then we are briefly introduce neural hardware architecture search. Can we not only do neural architecture search, but also do hardware architecture search to do such algorithm and hardware co-design? And finally, we'll give several applications that is improved by NAS. Okay. All right, so here are some references and papers. Feel free to reference them. And that's all for today's lecture.